you've not found that, okay, so where are we here? We are in Canopy. I guess shoot on back to your folks' class. There we go. Applied Calculus. Under Applied Calculus, go to the Math Lab tab. Then once you get to the Math Lab tab, go to the one where it's My Lab and Mastering Course Home. And I'm recording this, so if I'm going too fast and you're thinking, whoa, what happened? You can re-watch it. Of course, so at this point you can really get caught up. All right. If you take a look over here on the left-hand side, look at this one tab that's highlighted. Whoa, what's that say? Study plan. Get out of here. This thing has a study plan in it. It sure does. And you can work the study plan one of several ways. Either go through the recommendations, but a chunk of that will also include stuff that we've not messed with in the review section. Or you can just go ahead and go to the various chapters. Now, the nice thing about going to the various chapters is, if, for example, you're thinking, I want to brush up some on my limits. Well, that was in chapter 1. Oh, look, limits. Go to that section and, whoa, look at there. A whole bunch of questions on things pertaining to section 1.1. So there are opportunities to check out some homework problems there. And the homework problems are in a similar format to what they are in the homework assignments. Another way to go about this is you can, now does that make sense to everybody before I go zooming off in another direction? Another route is the e-text content. Go to chapter 1, and you could do chapter 1.1. Okay? You can get to the study plan there, or you can just go to the text. And I suspect or hope most people have been to the electronic text. Okay? At the end of each section in the text are the standard homework problems like what you would expect in most books. So there are a couple places for you to find homework problems, to find additional problems, to find ways to review for the test. If you don't like waiting for this thing to open, waiting, you can either go ahead and buy a copy for like $27. It's black and white and loose leaf. Or you can just use the books that are in the library. Okay? I'm guessing that the homework's going to be around page 112. We'll see what happens. There we go. Ooh, there was a guess. Okay. Yes, sir. It automatically does. Yeah. Okay. Okay. Yeah, what we're going to wind up doing on this homework stuff, because people are running into problems and this, that, and the other thing, is I'm just going to use it as a participation type grade, and we'll figure things out that way. Okay, so it'll be less painful if it didn't submit things and craziness like that for you. Hopefully it'll be fairer for you. But one of the things to be mindful of is if you're looking for additional problems, here they are. Is everybody good with that? Makes sense? Okay, so that's got that taken care of. What I want to do today is to take care of this chain rule stuff, make sure that this is working well for you. This is in section 1.7, I'm thinking. Or is it 1.6? I forget which. Let's see here. Boom, boom, boom. Let's see what section 1.6 is. One of the things we're going to do too here is very soon we're going to get into higher order derivatives. What's going to happen with the higher order derivatives is like, you know how we go through a problem, we get the first derivative? Okay? That's just the starting point. With that particular derivative then, we're going to take the derivative a second time. Oh. Think back to some of those quotient rule problems. We're going to be taking the derivatives of those. Okay? So we're going to have to be talking about some algebra and some maneuvers to do and just some ways to apply product rule as well as quotient rule, all in the same problem. And chain rule, which we'll get to. Okay? Yeah, so we are in section 1.7. Okay? So this is going to be section 1.7. It's a chain rule. Okay, chain rule is very important. It's the last of the main rules for us. What winds up happening is, at times, you have a function inside of a function. For example, let's say we're doing a quotient rule problem, and we have y prime equals something like this. I'm just making something up. X minus 3 times 2x minus 5 minus 2 times, 1/2 x squared minus 3x all over 2x minus 5 squared. So let's say it's the derivative of a function. We're going to want the first derivative because the first derivative allows us to locate maxes and mins. How do you locate maximum and minimum points with the first derivative? You set the first derivative equal to 0. Right. Okay, real fair question for the test. That's one of them. How do you locate max min? Set the derivative equal to 0. Another real fair question for the test would be, why do maximum and minimum points occur at locations where the derivative is 0? The derivative is a slope, and maximums and minimums are at locations where the slope is what? Horizontal line, tangent line, which means the slope is 0. Okay? So our maximums and minimums are always going to occur in places where the derivative is 0. We're going to move in a direction by January. It's going to take a little bit more machinery to get you working with that. We're going to move in the direction where you have multiple variables. Can't graph it anymore. And you're going to need to determine if that point's a maximum or a minimum, but you can't see it. How do you know if it's a max or a min if you can't graph it and you can't see it and things like that? Well, where the second derivative comes into play is determining if something is actually a maximum or something is a minimum. So we're going to need to be moving in a direction of being able to do higher order derivatives. Not just do the derivative, but do the second derivative as well. You'll need to be careful because with every problem then, you'll have something like y equals, you'll have y prime equals, and y double prime equals. You're going to have 3 equations. Each of these equations tells you something very different. The first equation, y equals, gives you the y value when x has some specific value. The first derivative gives you the slope, and the second derivative is going to tell you about concavity. We'll go further into that later, but basically that tells you are you at a max or a min point. And you're going to have to keep these things straight. You can do it. You do it on your car. Okay? I don't think you would ever get pulled over by a police officer and say, excuse me, ma'am, do you know what you were doing in that school zone? Well, I was fine. I had a full tank of gas. Exactly. What? What does having a full tank of gas have to do with your speed in a speed zone? You've got to be careful because you see those 3 equations? if you pick the wrong one, the answer that comes out makes every bit as much sense as saying, but officer, you can't give me a speeding ticket. I've got a full tank of gas. Okay? It might work, yeah. But I promise you it won't work in calculus. So you're going to have to be extremely careful to keep these things straight. Okay, there are like 3 gauges on the dashboard. One's a speedometer, one might be an odometer, and the other your fuel. Okay? So be careful about this. Be careful to label this stuff. Okay? And it's easy to drop labels just because you're in a hurry, but getting in a hurry can create problems. It might even be safe to do things like this is the slope, this is the concavity, and this is the Y value. Make the labels clear so that you know what you're working with in each case, because you're going to have all 3 of these things laying around, and all 3 of them are going to be laying around. As soon as we get to section 1.8, they're all 3 going to be laying around for the rest of the time that you're doing calculus. Yeah.
Does it say next to the second derivative?
I'm sorry. Concavity, concav. Yeah. Okay. So be aware that that's the direction we're heading. Now, when we go to take these second derivatives, we're going to have to be able to deal with derivatives of things like this. This is a scenario where you have a function inside of a function. You have 2x minus 5 inside of the squaring. Okay? One way to deal with taking the derivative of that is to square it out. You get your 4x squared minus 20x plus 25. Okay, when you square that out, you'll get that, and then from there you can take the derivative. In that situation, it's not horribly inconvenient to go ahead and perform whatever the outside function is. There are going to be a lot of scenarios, though, where performing the outside function is either impractical or impossible. For example, let's say you have something like this. Y equals the square root 5x squared minus 7x plus 16. Is there any practical way to apply square root to that quadratic? No. So, unless this was a perfect square, which it's not, if it was a perfect square, we could get it and be done. We can't here. So what we need to use on this then is the chain rule. And what the chain rule is going to tell us is, or be used in situations where you have an outside function with a function inside of it. Okay? So you've got an outside layer and an inside layer. And oftentimes I liken this to unwrapping a present. With a present, you've got the box and a wrapping paper and a ribbon on the outside, and what's on the inside? Whatever the gift is. Okay? Chain rule is for situations where you've got a gift. You've got an outside layer and you have an inside layer. Now you've got to be careful how you apply chain rule, because people have a tendency to shortcut it. With the chain rule, which you wind up doing, and I'll write the notation for it down here in a little bit, but the notation is sometimes more confusing than just seeing how it's done. First off, we can rewrite this as 5x squared minus 7x plus 16 to the 1/2 power. Chain rule, just like unwrapping a present. You only undo the outside at the first, right? You take off the ribbon, the bow, the wrapping paper, open the box. You only deal with the outside. While you're taking off the wrapping paper, are you also inside of the box looking at whatever's in there? Well, you can't be. You're on the outside, right? So while you're working on the outside, does whatever's inside change? No. So we're going to work first with the outside, which means the 1/2's going to come down, and we're going to wind up with to the negative 1/2. You're going to do a derivative just like you normally do for a power. Now remember, we're working on the outside, so while we're on the outside, does the inside change? No, it stays the same. So the inside staying the same is going to look like just bringing down the function that we have. Okay, so we're unwrapping this gift. We've got the wrapper, the ribbon undone, the box is popped open. After you've dealt with the outside part, now what do you deal with? The inside. After you've done the outside, now we do the derivative of the inside, which is going to be 10x minus 7. Does that make sense? Be really careful. What people are most frequently given to doing, and this is wrong, is to do that the derivative is equal to 1/2 to the negative 1/2. That's fine. But then they do the 10x minus 7 inside. Do you see the difference between those two? Okay, the second thing is wrong. It's wrong, 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 wrong. I don't want anybody to misinterpret me. That's wrong. Okay? I guess since we're in October, I can probably do something kind of like this. Okay? Okay? Now you know I went into math and not art. You kind of get the idea that it doesn't work. It's bad news. Okay? Be careful. Don't do that. Doing this as it's written in red is the same idea as dealing with the wrapping paper, the box, and what's inside all at the same time. Now think what that would look like. Somebody hands me a gift. It's nicely wrapped. I'm going to go straight from nicely wrapped to whatever's inside, which means I'm going to do something like right through the wrapping paper, the top of the box, and is that anywhere near appropriate? Okay? Depending on what's inside, I may now have garbage. Okay? So remember, don't do it that way. People are real tempted to do it like that, and it never works. Okay, so let's try another example, something like that. Let's say we have something like y equals 1 over, let's say 3x squared minus 7x plus e to the x raised to the 8th power. Does that denominator look like something you want to raise to the 8th power by hand? Yeah, I got the rest of the afternoon. Let's go for it. Okay? That's a mess, isn't it? There are two ways to handle this. One is with the quotient rule. But if you'll recall, when we were doing the quotient rule, I mentioned that there's a second way to handle a lot of rational functions that's less painful than the quotient rule, and this is one of those cases. We can take this and we can rewrite this as this 3x squared minus 7x plus e to the x raised to the negative 8 power. Does that make sense? Instead of dealing with it as a rational function, I'm going to rewrite it taking advantage of the exponent. Now what we have is a function raised to the negative 8th power applied to something inside. Oh, this is similar to what we just had before, isn't it? At this point, then, you can do the derivative fairly painlessly. The derivative will be negative 8, whatever's inside. Let's see, be careful. Is it going to be to the negative 7th or negative 9th? Negative 9, isn't it? Because you're subtracting 1. Minus 9, we're going to have our 3x squared minus 7x. Yeah, I was thinking I'm also going to do the second derivative of this. There's part of it. It's not done yet, though, is it? We've taken off the wrapping on the outside, but what do we still need to address? The inside. So we're going to have 3x minus 7. What's the derivative of e to the x? E to the x. That's a fair question for the upcoming test, isn't it? Prove that the derivative of e to the x is e to the x. And really, that was basically just two steps, wasn't it?
Can I write that e to the x?
You can. It'll get you 0 points, but rats. Okay? So here's the derivative. Now, I mentioned that very soon we're going to be going to second derivatives. which is why I jotted down the second derivative before. And with your keen eyes, you noticed it. How are we going to take the derivative of this mess? Overall, it's a product rule, isn't it? You got two things being multiplied together. So what you need to do is to first say, okay, this whole chunk here is what we're going to call f. And then this factor here is what we're going to call g. Maybe a little bit on the thin side. So when we do the product rule, we're going to have f prime times g plus f g prime. And I don't know if it'll fit on one line, but we'll find out. Okay, so we got things laid out. We're just going to take them one at a time. The first thing we need to do is to take the derivative of f. Well, it's going to be that negative 8. How are we going to take the derivative of that mess? It's a chain rule problem, isn't it? Do you see that? Does that make sense to everybody? That first part there is negative 8 e to the 3x squared. That whole business raised to the negative 9 is a chain rule. Does that make sense to everybody? No big surprises there? So when we do the derivative, we're going to have the negative 9 as the exponent coming out front times the negative 8, which is going to give us a positive 72. The inside does not change. Subtract 1 to the negative 10th. Continuing with the chain rule, we're going to have 6x minus 7 plus e to the x. Does that make sense to everybody? All of that is f prime. And we now need to multiply it times what? Times g. Which is going to be, have we seen this before? 6x minus 7 plus e to the x? Yeah. So there's the first part. Is that the whole product rule done? Nope, that's just the first half of it. Plus, then we need to just write down what f is. So that's going to be this negative 8 times this 3x squared minus 7x plus e to the x raised to the negative 9th power. Then we're going to write down what the derivative of g is, which is going to be 6 plus e to the x. These answers are going to start to get long. Is everybody okay with how that works? Okay. Now, this one portion here, this could be written as 6x minus 7 plus e to the x, all raised to the second power, since you have that factor times itself. You could rewrite it like that. Oh, this stuff's getting a little long, isn't it? Chain rule can get entertaining. Let's take a look at another example. Let's say we have something like y equals the tangent of 7x cubed plus e to the x minus 3. And you need to compute the derivative of that. This, once again, is a chain rule because you have an outside function being applied to an inside function. The outside function is what? Tangent. And the inside function is that 7x cubed stuff, isn't it? When you take the derivative of this, okay, when you take the derivative of this, the derivative of the tangent is going to be, what is the derivative of tangent? Secant squared. So we're going to get secant squared of this 7x cubed e to the x minus 3. Now keep in mind, secant squared can also be written and really means you figure out whatever that value is and then you square it. Okay? Figure out whatever the value is inside and then you square it. When we go to evaluate this. Not done with the derivative yet. We've got the outside part taken care of, the wrapping paper, the bow, and the box, but now we've got to get the inside. And the derivative of the inside is going to be 21 x squared plus e to the x. There's your final answer. Do you need to simplify that? No. One of the things I do want to point out to you, the way it's written here means something very different from leaving those brackets out. If the brackets are left out, now it's getting squared. Yeah, only the 7x squared stuff, not the secant. So you've got to start to be very mindful of where you put your brackets and things like that. This is also why, for your trig functions, they've gone to notation like this to mean that the whole thing is squared, so that it doesn't become confusing on if we're just squaring the argument's the stuff inside, or squaring the whole thing. So that's why the notation goes to putting the exponent next to the secant, or tangent, or sine, or whatever it might be. Please?
Would you accept either?
I'll accept either one. Yep, they're both fine. So if you write it like this, great, I'll take it. If you write it like this, great, I'll take it. If you write it like this, not so much. Okay, because that means something very different. Make sense to everybody? You all good? Okay. Not going to bother doing the second derivative of this one, because that would be like a lot of work. Maybe someday in the near future. Okay, let's take a look at another example here. Let's do something like this. Let's say we have the cube root of 5x minus the sine of x, the whole thing to the 5th power. And you're asked to compute the derivative. Go get them. See what you can do with that. See what you can do with that. You're welcome to chat with each other. All right. Okay, gentlemen, what's the first move on this problem? The first thing you do toward taking the derivative, what's it going to be?
5/3/3.
Yeah. Now, you can do that in 2 stages or 1 stage. Right now we have this 5x minus sine of x raised to the 5th, and we're doing the cube root of that whole deal, aren't we? When you have a power raised to a power, what do you do to the 2 exponents? You multiply them. So this can be rewritten then as is 5x minus the sine of x raised to the 5/3 power. Does that make sense? The first move here is getting this into a form that we can even start to take a derivative. Does that make sense to everybody, or is anybody lost? Now that you have that, we're going to do the outside layer. Okay, that means we're going to bring down the 5/3. I'm going to leave whatever's inside alone. And I'm going to subtract 1 from the exponent. 5/3 minus 1 is 2/3. Because 1's the same thing as 3/3, so you have 5/3 minus 3/3. Now that we got the outside part done, we can do the inside. The derivative of 5x is 5 minus, what's the derivative of sine? Cosine. And there it is. Should you simplify this? No, leave it alone. Leave it alone. Because there's nothing there that clearly will combine easily to make it any cleaner, is there? Now the catch is very soon, section 1.8, we're going to have to do the second derivative of that. Okay? But we'll save that for Monday. Why? It's important because we can find critical points. Critical points can either be maxes or mins. But we don't know which it is. The second derivative will allow us to determine which it is. Because I do not want to send you off to P&G with a nice job only to discover, geez, I've been minimizing the profit for the division. Is that a problem if you're at P&G and you're minimizing the profit instead of maximizing it? Yeah, you're going to be out on the street real fast. Okay? So we want to get that also straightened away. And we're going to be in situations where you can't graph it. You can't tell. Okay? Now, Gabby asked, she said, wait a minute, while I was checking around, she said, remind me again, Chuck, how is it that the derivative of e to the x is e to the x? So let's do a quick infomercial. Here, let's pick this color. Okay, so if you have y equals e to the x power, e to the x can be expressed as a Taylor series polynomial. Say what? It can be written like this: 1 plus x plus x squared over 2 factorial x cubed over 3 factorial x to the 4th over 4 factorial, and it keeps going. Does this look sort of familiar from somewhere? If we take the derivative is going to equal. Now what we're going to do is term by term compute the derivative. What's the derivative of 1? 0. Plus, what's the derivative of x? 1. Plus, x squared is the same thing as 1 over 2 times 1. Okay, so that x squared over 2 factorial can be written like that. When you take the derivative, you see the 2 in the exponent? It comes over and it multiplies times the fraction, doesn't it? So what you'll wind up with is 2 over 2, and 2 over 2 has a value of 1. So we'll have 1 times x to the first power, which is just going to be x. Plus, going to the next term, this 1 over 3 factorial is 3 times 2 times 1. It's an x cubed. When you take the derivative of that, the exponent, the 3, is going to come over and multiply times the 1 over 3 times 2 times 1, isn't it? And what it'll give you then is you'll have a 3 in this numerator. The exponent will become a 2. The 3's cancel. This can be rewritten as x squared over 2 times 1 is 2 factorial. The next term, okay, x to the 4th, 1 over 4 times 3 times 2 times 1. When you take the derivative, you're going to get a 4 here. The exponent's going to become a 3. The 4's cancel. Make sense? Which is going to give you x cubed over, what's 3 times 2 times 1? Isn't it 3 factorial? Plus, and it continues like that, term by term by term. And when you get this polynomial back, that's equal to what? E to the x. Very good. So that gives you back your e to the x, which then demonstrates that the derivative of e to the x is e to the x. Bless you. Is everybody good with that? Not too horrible? Yeah, with a little work, it'll get there. Okay? It's really pretty cool once you get comfortable with it. It's a pretty slick move. And it's one of the easier proofs we're going to do all year. Okay? So that's about as easy as it gets. Hey, what's the other one that we did the other day? It was proving that the derivative of tangent is secant squared. Yeah. Oh, that's right. Proving that. Yeah. Be sure that you can prove that. How would you handle something like this? Okay. Let's say it's something like y equals square root of 7x minus 4. And you're asked to compute the equation of the tangent line. At the point, let's see here. Well, let's just say at x equals 1. There. Go get them. Yes, sir.
I have a question on the homework, by the way.
Okay.
It was like e with a line on top of it, and I did not know how to do that.
Okay.
Can you explain how to do that?
So is 1 over the square root stuff?
Here, I can
Okay. Well, while you're pulling that up, how would you do this one? We got to do the equation of the tangent line at x equals 1. This is going to be an important move. Okay? Hang in there a second, Roger. We'll get to it. I promise you, we'll get to it. How do you... what are you going to do here to get the equation of the tangent line? Yeah. Remember, you're going to need y equals mx plus b. Right? That means that the first thing we need to do is we need to compute the slope. Well, the slope means that we need the derivative. Y prime equals, just like with the earlier ones, this can be rewritten as 7x minus 4 to the 1/2 power for y, which is going to give you y prime is going to be 1/2 7x minus 4 to the negative 1/2 times 7. Does that make sense to everybody? I did that using the chain rule. Okay, there are two things that we need. One, we need the value of the slope. The slope at x equals 1 is going to be equal to 7 over 2. Now, this raised to the negative 1/2 is going to be 1 over 7 times our x value minus 4, and there's going to be a square root there. Does that make sense what I just did? Okay, let me rewrite that. Yeah, it's not letting me erase. Okay, so I'll rewrite it bigger here. Now it's not writing. There we go. Y prime of 1 equals. You've got the 7 and the 1/2. Those will multiply together to give you 7 over 2. Times. Notice the exponent's a negative. That means it's going to the denominator. We've got a 1 over. The exponent is a 1/2. That's a square root. The function that's inside the square root is going to be 7 times whatever x is minus 4. What's the value of x in this particular problem? 1. So you plug a 1 in here. So this is going to give you 7 over 2 times 1 over the square root of what? 3. Which is going to give you 7 over 2 square root 3. You can rewrite that as 7 square root 3 over 6, rationalizing the denominator. Now, 7 root 3 over 6 is the what? Slope. Okay, so this gives us part of the information that we need. So we're going to have in our equation y equals 7 square root 3 over 6x plus whatever the value of b equals. We've got to solve for b. How are you going to solve for b? Okay, we got to plug something in. We know our x value is 1. So what we can do in solving for b is we can take this value and plug it in for x. We need the value for y. How are we going to get a value for y? Okay, yeah, you were given x. Y isn't given to you here. You're going to plug x into the original function. Remember I said be careful. You're going to have multiple equations laying around that you need to use. Here's one of those scenarios. We need to know y at x equals 1 equals the square root 7 times something or other minus 4. And that something or other is going to be the x value of 1. So our y value is going to be square root of 3. Are you okay so far? Okay, so we know the slope. We know the value of y. We know the value of x. We need b. Well, you get that by doing y equals mx plus b. Y is square root of 3 equals, the slope is 7 square root of 3 over 6. X is a value of 1 plus b. Be nicer if we had numbers like 2 and 5, wouldn't it? On occasion you'll get those again and you'll come to appreciate them. What on earth are we going to do with this? Well, let's see. We want to get b by itself, right? So I'm going to subtract this 7 square root of 3 over 6. So that's going to give me the square root of 3 minus 7 square root of 3 over 6. Remember, this is over 1. Oh, we can get a common denominator, can't we? That'll make this then 6 square roots of 3 over 6. So what's b going to equal? Negative the square root of 3 over 6. That makes sense? You've got 6 of them, subtract 7 of them, and you wind up with a negative 1 of them. This then gives us our value for b, which is going to be a negative square root 3 over 6. With that being a negative, we can get rid of the plus and this minus business here and just write it as minus root 3 over 6. And that's the equation of the line tangent at that point. That one takes a little work, doesn't it? Now, Raj, what is the homework problem that we need to tackle?
It's about rate of change,
Okay.
average profit.
Okay.
I don't know what to do.
It's okay if I grab your computer quickly and read it? Okay. This is from section 1.6, number 57. And what it tells you is an accessories company finds the cost and revenue as follows. The cost is going to be 710 plus 30x minus 0.065x squared. And the revenue is going to be 35x raised to the 9/10. Determine the rate at which the average profit is changing when x equals 171. So we want the change in the average profit. Yeah, that one's kind of ugly. Okay, first thing we got to do here. After safely handing that back over, we've got to get a profit function. What's the profit function for this? It's going to be P of X equals. How do you do profit? Revenue minus cost. So what it's going to be is this 35 x to the 9/10 subtract the cost, which is this 710. And for time, I'm going to distribute the negative sign as I copy this down. Minus 30x plus 0.065x squared. That's your profit function. But you got to be careful because on this one it doesn't ask for profit, it asks for what? Average profit. The way you compute average profit is the same way that you do any other profit or any other average. You take whatever you have and divide it by how many of them you have. Does that make sense? So to get the average profit, I'm going to take this profit function, 35 x to the 9/10 minus 710 minus 30x plus 0.065 x squared all over x. Now, you're asked what is the change in average profit. The derivative tells you the change. The derivative's the slope, isn't it? Okay? Remember, derivative is slope, and slope tells you how things are changing. So what we now need to do is take the derivative of that. Two ways to do this. One way is the quotient rule. Oh yeah, that looks like fun. Another way is to remember that if you have something like this, 3 plus 5 over 2, you can rewrite that as 3 over 2 plus 5 over 2. Right? So what I'm going to do is split this up into individual chunks. 35x to the 9 over 10 over x minus 710 over x minus 30x over x plus 0.065x squared over x. And the advantage to doing this is on a number of these terms, things simplify. For example, see the minus 30x over x? The x is canceled. The x here cancels with this one. This will cancel with this, leaving you with a negative 1/10. Now, we haven't actually gotten to the point where we can do the change, but we do now have 35 x to the negative 1/10 minus 710 x to the negative 1 minus 30 plus 0.065x. And can you do the derivative of that? Yeah. Notice, how much calculus have we done so far? None. All of the hard work here is the algebra. Here, I'll move that down a little bit, Gabby. That may help on the picture. Okay. At this point, you take the derivative. And when you get the derivative, you plug into 171. Now, what that'll tell you is, if you go from making 171 of them to making 172, how much has the profit changed? It might go up, it might go down. Does that make sense? That's a real quick answer on that one, Raj. Hopefully there's enough there to help you out on it. Okay, folks, I'll see you all Monday. Your quiz is up here. Yeah. There you go. It's due Monday. All right. You're not allowed to use your book, your notes, or the math lab.